Hello, everyone. Welcome to Project WaveDancer. We are Team Bella Labs, and I'm Kaku, and I work with Maya, Jack, and Tentai. And Noah is the sponsor of our project. First off, the problem we are facing is that the southern resident killer whales population has stayed at a dangerously low level for over 50 years. So the researchers at NOAA are trying to find out the reason and try to help them to protect their population. And by studying at the hormones and bacteria present in whales' respiratory system, researchers are able to monitor their overall health. Here are some methods they've tried to collect samples from whale blood, but the problem is that they couldn't collect enough volume of sample. So here it comes to our problem statement, is that how can we design, build, and test a drone-mounted breath collection device for southern resident killer whales in order to help NOAA researchers better understand their overall health in order to shape policy decisions. And we have three main design requirements. The first one is that we need to make sure the drone is easy to control. And the second one is that we need to protect the collected sample from evaporation. And finally, we need to increase the collection volume by creating a device with a large surface area.
Okay, so obviously it wasn't going to be feasible for us to charter a boat and find an orca whale every time we wanted to test the prototype. So the first thing that we had to do was make an artificial blowhole. So we characterized the duration, size, volume of a typical orca whale's blow plume, and then we made a kind of simulated environment for that. So here you can see we've got a modified pressure washer. It's actuated via stepper motor that's controlled via an Arduino. And so we would kind of fly through those plumes to test our various prototypes. So when we were initially starting out, we took kind of a wide shotgun approach to just test a bunch of different ideas. So we had possibly an array of petri dishes, a petri dish where a servo motor could cover it. We had a Nitex kind of windsock, as well as a vacuum device. And we were just kind of throwing a bunch of ideas at the wall and seeing what stuck. The solution that we got to is a clamshell design like this. So you're getting a ton of surface area. It's able to open and close so that you can prevent evaporation and contamination. It's controlled remotely. So this is communicating via LoRa. And then the shells themselves are easily swappable so that researchers can do one pass, move that into storage, set it up again, and go out and do another pass. Our larger components are made out of carbon fiber to keep everything as light as possible. Sumaya is going to talk a little bit about how we got there in a second, but I'm just going to show you one more thing. Here's kind of the nuts and bolts of how it works. We've got a 20 kilogram servo motor, and that is able to open and close that clamshell under a variety of windy conditions. All of that is powered via a couple of batteries.
Okay. Throughout our journey working in this project, we did different kinds of testing, starting with interviews. We interviewed drone pilots who worked with NOAA in collecting blood samples from southern resident killer whales. And the main highlight here is that the device should operate quickly and easy, and it has to be easily swappable. After that, we conduct usability testing with people who have experience in flying drones to test assembling the device and flying the drone with the device attached to it. And we found out that we have to change mounting mechanism to a griddle, and we have to reduce the payload to increase flyability. And to quantify the payload, we test the effect on different payloads on the drone's motor temperatures. And we found out that the payload should be under 250 grams in order to keep the drone's motors in a safe temperature and not affect the flyability. After that, we did a series of functional testing to find out the best way to mount the device, the best mounting mechanism, and the mounting location. And the results indicate that the device should be less than 300 millimeters away from the drone with a rigid mounting. And with the flexibly mounting, it affects the drone nimbleness. Regarding the mounting location, we found out that the collected amount is the same above or below the drone, and that the mounting location just needs to be away from the existing sensors. Finally, to find out the best way to collect more samples, we test all the different prototypes that we built, which I already talked about, by flying the drone over the blowhole that we built, and then scale the amount that we collected and compare them. And we found out that increasing the surface area increased the amount collected and evaporation was an issue. And as you see here in the graph, our clamshell prototype was able to collect as 3 times as much as the current approach 1 Petri dish. Here is our hardware architecture. We are using ESP32 for both the controller and the collection device. And when the button is pressed on the controller, they're both communicating through LoRa. So when the button is pressed and the controller is going to send a signal to the collection device, which is going to trigger the servo motor to open and close the clamshell. Here I'll go through a simple user scenario to show you how the product works. So first, the drone pilot is going to get the device with instructions on how to attach it to the drone. They're going to follow it and try flying the drone with the device attached to it. And when they are in the open water and find a whale, they fly the drone with the clamshell closed, and then they're gonna open it and fly the drone over the whale's floor. After that, they're gonna close it and fly the drone back to the boat. In the boat, they're going to land the drone, take the clamshells that already used and put it in a cooler and add a new one and do the same process again. And when they're collecting enough samples, they're going to send them to biomarine researchers who's going to process them.
All right, so this photo here is just a few of our different prototype iterations. 10 that we had on our team is that every idea we had was tried at least once. You can see there on the far left, we sort of have more petri dish-like designs, which then evolved from the ones you see on the right, which was our final sort of rectangular clamshell. Here is a really unique prototype we had, which was a vacuum pump used to suck up the whale's aspirant. However, in the tests we had with our simulated environment, this didn't provide as much sample as the other petri dish or clamshell-like designs did. Here's a quick map of how we sort of tested and iterated over time. You can see there, far left, we just had simple petri dishes attached to sticks and motors that open and close. But from testing, we quickly found that surface area is ultimately king. Just the more surface area you have on our device, the more water you can collect. There at the bottom, you can see we had started with a single-use vacuum, which then evolved into a very large, almost dome-like shape, which had 4 vacuum pumps and 8 entrances for samples to be collected on. So the value that we bring is that we can collect more sample without endangering any of the whales or any of the researchers. And we could also expand current designs to fit all sorts of different kinds of new use cases like environmental sensing or greenhouse gas emissions. The next question is, what's the economic benefit of this? The ocean accounts for about $1.5 trillion of global gross value-added economic activity. And as many of you may know, orca whales serve as a very important predator in the ocean ecosystem. We also do realize that it's unlikely that this would make for a successful private for-profit business. And so government organizations such as our sponsors, NOAA, they're the ones who fund groups like us in order to complete research and to make devices like the ones that we have. Now for the next stage of development, should this project go on any further, a few of the things that could be done first is more real world testing. We have a pretty accurate simulated environment, but that is absolutely no replacement for going out on a boat and actually having that experience of flying over open waters. Next is refining our electronics a little bit, higher capacity batteries, smaller circuit boards, and finally finding out a more elegant storage solution for a device so it doesn't need to be taken on and off constantly. Now, in lieu of flying our drone inside, we have a quick demo for everyone.
Here, you can see our device attached to a consumer-level DJI Mavic 3 drone. In this scenario, the drone is launched by hand to make takeoff easier from a moving boat. After takeoff, the drone tracks the whale with the collection mechanism in a closed state. This both prevents contamination and reduces drag. Upon seeing the whale surface to breathe, the drone pilot opens the clamshell mechanism, swoops through the plume, and then closes the device. This action is done manually via a remote controller. The drone then flies back to the boat, where it is then caught by hand. Catching by hand is necessary when trying to land a drone whose position is fixed via GPS onto a boat that is constantly moving relative to it. Once landed, the researcher uses a couple screws on the back of the mechanism to swap out the clamshells, putting the used ones into storage for transport, and setting up the device with a fresh pair to go back out for another pass.
As this is our last presentation, some special thanks are in order. On behalf of the team, I'd like to thank our NOAA sponsors, Jennifer Tennyson, Linda Rhodes, and Brett Hansen. They were all fantastic in helping us out. And of course, also thank you to the teaching staff, John, Linda, great help and great feedback during this entire process. And one more big thank you to the team that's coming up next, actually Team Firebot. They bankrolled and built the drone lab so we could test indoors and not outside of the Seattle winter. That's going to be it for us. Thank you, everyone. Have a wonderful rest of your evening.
Thanks, team. And while we're waiting for questions, just one more shout out. Kaku, who joined us online, has done the entire program from China and even built his own prototyping labs where he was present, so that he built some of those fancy vacuum prototypes. So thanks to Kaku for that engagement. All right.
Thank you.
I just wanted to say this is a great project and really, really interesting. Actually, when I was a student in undergrad at UW, I also worked with NOAA on a project, but it was for monitoring crab larvae. So I know how important, like keeping the health of the ocean in mind is. With that in mind, a quick question on your collection mechanism. I really liked the design. So is the idea that this carbon fiber apparatus just gets just holds the water vapor inside, and the researcher will just collect the water off of the carbon clamshell?
Yeah, exactly. So we have different liners that we can put in there where it can be the same liners like a petri dish or silicone. The droplets that we're collecting are really, really fine, and like 2 milliliters of collection is like a good pass through. So it's essentially just getting misted. It's not pouring off by any means. But yeah, exactly like you said, we're just collecting it in that surface right there.
Yeah.
So I used LoRa for a project earlier in the program. I'm just curious if you guys were able to test or found any research about like the relative range of LoRa out on the open water to seawater.
Yes, we actually specifically tested the LoRa boards that we intend on using for this. And through testing, we actually found that the LoRa range is far beyond the range of the controller that's used to control the drone. So we believe this won't be an issue, especially out on open water. There's going to be nothing obstructing, especially if you still maintain line of sight. I think just here doing tests from this building, we were able to get about 250 meters away and still get a reasonable LoRa signal.
And you get a little bit of delay after that, but it still talks.
Really impressive project. So I noticed like in the prototype that's shown here, you have the collection mechanism underneath the drone, and in the new one you have it above the drone. So how does that, like, what made you like decide to put it above, like, and how does that affect the drones, like, maneuverability?
So from our testing, we initially were thinking about where to move it because we were worried about the turbulence from the roadways affecting how much you collected. In the end, we determined that it really didn't matter where you put it. But what we were really trying not to do is occlude any of the sensors that were already on there. So there's a lot of object avoidance sensors that are built into it, and its final location just happened to be kind of in the blind spot of all of them.
Perfect, thank you.